This is part of our video series on human-centered evaluations for NLP explanations. Check out the link for more resources. You're currently here.
Thanks, Allison, for the crash course. I will now apply what we've learned to some use cases to show how to design human subject studies to evaluate explanations. Recall the taxonomy of prototypical use cases of explanation I introduced earlier. I will focus on the first three. I also mainly focus on the first two steps of experimental design, thinking through the treatment designs and choice of evaluation construct and measurements, including use case outcome, model understanding, and other effects. I will use experimental setup in some published empirical studies. As you may have noticed, we always include a reference at the bottom of slides, so if you're interested in the details of these studies, you can look up these papers. However, I will adapt the measurement based on these three sets of evaluation constructs, since this original paper was either not purely evaluative research or only focused on a subset of constructs. So let's start from the first common use case of explanation, decision support. I will adapt the setup in Lai and Tan's FACT 2019 paper. So the study used a deception detection task to study the effect of input attribution explanation to support human decision makers to judge if online reviews are deceptive. Recall this kind of explanation highlight the keywords in the content as the difference maker that lead AI to predict whether the review is deceptive or not. Here, the treatment design is to compare the effects of show explanation versus not show explanation. So you would need two conditions for the experiment. A baseline condition where the AI is used to support deception detection without explanation, an experimental condition with the same AI but showing explanation. You would recruit participants and randomly assign them to one of these two conditions and ask them to perform the deception detection task. You would collect data from the two conditions and compare the results. Now, what construct would you be comparing on? We should always start with the use case specific outcome. In the case of decision support, it is the outcome of the decision of the human AI team, the decision performance. Recall that Allison discussed the use of objective and subjective measurement. It is important to have objective measurements of task outcome. As you have the ground truth label of the correct decisions, you can measure the human AI decision accuracy easily. You can use other common performance measurements such as precision, recall, false positive, false negative, and so on. You can get such measurement for each participant, then compare the performance between participants in condition 1 and condition 2 by a statistical test, then conclude whether show explanation improved the decision outcome. One subjective measurement you may be interested in for decision support is to ask participants to report their subjective confidence in their decision. This can usually be measured by the survey question after they make each decision or after all the decisions in an experiment. Sometimes you may discover that explanation could improve people's confidence in the final decision. This is usually a good thing if the explanation did also improve the objective decision performance. Otherwise, you might want to worry about the potential risk of overconfidence for downstream usage. In some studies, you may have seen the evaluation of reliance. Reliance on AI is directly related to the decision outcome, and the measurement of the two are often highly correlated. But you may choose to focus on reliance if you are more interested in how explanation impact the outcome of human interactions with the AI. In the most common decision support workflow, the AI gives a prediction, then the human chooses to rely on it or not. Here you can measure the objective reliance by the agreement percentage, the percentage of decision where the human's final decision agreed with the AI's prediction. In another workflow, the human first gives their own judgment and then sees the AI's prediction. In this case, you can more precisely measure the switch percentage by looking at the percentage of switching to AI's prediction for cases where the human and the AI initially disagree. Note that switch percentage can be a more reliable measurement since it explicitly gauges if a human would have made a decision differently without AI. However, the workflow may not be a realistic one for most AI decision support tasks, so there is a trade-off you may want to consider and acknowledge. You can also choose to measure appropriate reliance, which would give you a more precise understanding on if explanation improve appropriate reliance or lead to the problems of over or under reliance. The key is to separate cases where the AI's decision were right and were wrong based on the ground truth labels. Appropriate reliance is the percentage of cases where the human either correctly followed the AI when it was right or correctly rejected it when AI was wrong. Over-reliance measures the percentage of decision where human incorrectly chose to follow the AI when it was wrong, whereas under-reliance measures the percentage of decision where the human incorrectly rejected the AI when it was right. I want to briefly touch on the measurement of trust. Reliance is by definition an objective action. Trust is by definition a subjective attitude. Sometimes people mix the two terms. It is important to recognize that reliance can be guided by trust, but trust is not the only factor that determines if one will rely on AI. For example, people's self-confidence and time constraints can also impact reliance. You may choose to measure both in a study, but reliance and trust are two different constructs. If you're interested in measuring trust, one common approach is to use survey items that self-report trusting belief, whether one believes the AI is capable, well-intentioned, and predictable, and or trusting intention, whether one would like to keep using or count on the AI. These measurements are adapted from the classic work by McKnight et al. On trusting e-commerce. Now let's talk about measuring model understanding. It is often useful to evaluate whether explanation improves model understanding because it directly tells you if people are gaining useful information from the explanation and sometimes can help you diagnose what they're not learning from the explanation. Again, it can be measured by both objective and subjective measurement. They do not always align in the results, and a discrepancy between the two calls for consideration of potential issues. For objective measurement of understanding, you can design some factoid question about the model for people to answer after the task and score their answers. You can also adopt the simulation task I mentioned earlier as a proxy task. You can modify them to test people's model understanding after experience explanation in real tasks. For example, you can give a new input and ask people to simulate the model output, or give an input and output and simulate counterfactual cases asking what if some feature change, or what needs to be changed to get a different output. If the explanation did help understand how the model works, they should be able to simulate model decision on unseen cases effectively. You may find some example tasks designed in this KITE 2019 paper by Cheng et al. I referred to at the bottom. For subjective measurement, it is straightforward to ask people to self-report if they feel they understand how the AI works with the Likert scale. What else matters for decision maker? I want to mention two things, and you can find other measurements in this recent survey paper by Lai et al. On empirical studies of human AI decision making. One is decision efficiency, which can be measured how much time one spent on making the decisions. The other is cognitive load, which is commonly measured by a subjective questionnaire called NASA LTX. Some explanation forms may significantly increase the required time or cognitive load for decision makers. Those can be the downsides to apply them for decision support use cases. Now let's move on to a second use case, model debugging. I would like to introduce this experimental setup used by this KITE 2020 paper by Kaur et al. Again, I'm going to adapt the measurement use, especially since this paper is more of a qualitative study. In this setup, let's consider a different kind of evaluation treatment design. Instead of evaluating whether one type explanation is effective, You're interested in comparing two types of explanation. One is explanation generated by a directly interpreted model called GAMS, and the other is a post hoc explanation generated by an algorithm called SHAP. So you would create two treatment conditions, one for each type of explanation. You can also create a third control condition with no explanation at all. You would recruit participants. Here they should be machine learning engineers who know how to perform model debugging tasks, and randomly assign them to one of these conditions. For use case specific outcomes, you will be interested in the outcome of model debugging, that is, the model improvement from debugging. It is straightforward to measure the final model performance and compare that between the conditions using different explanations. You might also want to zoom in the debugging process and examine the number of bugs identified by participants and the number for different types of bugs. A trick you can use when designing the study is to manually incorporate different types of bugs in the initial model as the ground truth. This will also give you more control to comprehensively examine the effectiveness of explanation in helping identify and improving different types of bugs. Similarly, as for the decision support use case, for subjective measurement of debugging outcome, you can ask participants to self-report their confidence in the model readiness after the debugging task. Model understanding measurement can be similar to what we use for the first use case, including factoid question, after-task simulation task, and subjective understanding. I want to mention another useful type of measurement that was adopted by the Cao et al. Paper, that is by qualitative methods, based on how people describe how they think the model works. A very useful approach is contextual inquiry, asking people to think aloud or prompting them to describe their beliefs, ideally when they are performing the task. You may then transcribe their answers and perform qualitative content analysis, for example, by rating the correctness of their descriptions, then comparing the results across conditions. What else matters for performing model debugging tasks? You may consider things like efficiency, easiness to learn, how to use the explanation, and the perceived utility of the explanation. The last two can be measured by questionnaires. Now I want to quickly discuss a third use case. That is to use explanation to audit for model fairness issues. This is a study that we published at IUI 2019 led by my collaborator John Dodge. So we used a recidivism prediction task. That is, the model suggests if a defendant is likely to reoffend, to assist the human decision maker, realistically the judge, to make a bail decision. We conduct a study asking participants to audit if the model is fair or not. We compare the effectiveness of 4 types of explanation: contrastive, which is a type of counterfactual explanation, example-based, global feature importance, and data distribution-based explanation. I want to mainly discuss the outcome measure of fairness auditing here, as it illustrates the complexity that sometimes you need to design into the experiment to get the right measurement. Here for this auditing use case, what you care about is not just people's fairness judgment itself, but its calibration with regard to the ground truth of the model being fair or not. To capture calibration, you would need to create multiple versions of the model. Some are more statistically fairer than others. If an explanation is effective for supporting auditing, it should help people differentiate between them. So to measure it, you would then ask people to read this model separately and then measure the distance between their rating for the fairer and unfairer model. This distance is the measurement for the construct of fairness calibration. If you want to compare the effectiveness of multiple types of explanation, you would want to capture this distance measurement for each explanation and compare them. So in that study, we ended up having 8 conditions for the 4 types of explanation with 2 levels of statistically fair and unfair model. Thanks for your attention. Here is a summary page with some suggested evaluation construct you might consider for the 6 prototypical use cases of explanation. This is not a complete list, and you don't have to always measure everything. The choice of measurement will always depend on what you care about and how much resource, whether it's your time or your participants' time, can afford. What you care about may be determined by how specific your research is to some application, what matters for the application, and how high-stake the application is. The takeaway, I hope, is that there are different use cases where people seek AI explanations, and there are multiple facets of effects of explanation on people. As a field, it is important to conduct human subjects, human-centered evaluation to understand where and how different explanations thrive or fall short. And that requires studies with ecologically valid experimental setup and carefully designed measurements.
This video isn't the end. You're currently here. If you're lost, click on the link below for source code, slides, and other resources.